Magnetic reconnection is the process of disconnecting or connecting the magnetic fields to each other, directing energy into the Earth on the day side and then letting it go on the night side. And the interplay between those two is what produces all the space weather around the Earth that has big effects, can damage our spacecraft, can hurt astronauts, can upset the flow of electrical energy in our electric grid on the surface of the Earth. MMS is a mission with 4 spacecraft that are traveling in formation in an orbit that takes them out into 2 special places near the Earth, one upstream toward the Sun, one downstream away from the Sun. Both of those places have magnetic reconnection. We have never, before MMS, had the ability to essentially run the camera fast enough to catch it as it goes by, to make mini measurements per second. The science payload for MMS is all mounted on a single deck plate, but it consists of some 25 boxes per spacecraft, divided into 3 general groups of instruments. And that's those for measuring fields, electric and magnetic, those for measuring plasmas, and a third for measuring energetic particles. The magnetic field sensors are out on arms that extend away from the spacecraft. They're fixed, but the spacecraft is spinning slowly, about once every 20 seconds. The electric field is quite a bit different. It consists of 4 wires that extend out away from the spacecraft with a ball on the end of each of them that actually contacts the plasma. All 4 of those are spinning around with the spacecraft at this 20-second period. And then there's a third axis that extends, their booms that extend along the spin axis of the spacecraft, both upward and downward, with a probe at the end. So you've got 3 components of the electric field. They can measure everything from up to small wiggles and vibrations of the electric field. There's another sensor called the search coil magnetometer that is just a loop of wire connected to a suitable amplifier and is designed to measure the fluctuations at higher frequencies than you could get with the DC magnetometers. For the plasmas, there are 8 boxes, 2 boxes at each of the 4 points of the compass on the spacecraft. Those are equally spaced all the way around the spacecraft, essentially. That is a real key ingredient for being able to see the entire sky instantaneously without waiting for the spacecraft to spin. Then there's also a hot plasma composition analyzer, 1 per spacecraft. It has a sensor head that looks all around in a 360-degree annulus, sticks out the side of the spacecraft and sweeps out the whole sky twice per spin. It measures the chemical species of the particles. The third set are the energetic particles analyzers, and they are measuring much more energetic particles that are accelerated by the reconnection process. Ultimately, the thing we will be doing is comparing our observations with simulations of the entire magnetosphere as it is influenced by the solar wind coming in, down to the details of what reconnection is occurring. People who do those simulations that try to apply them to all other kinds of places, like in the solar atmosphere, other astrophysical stars and other objects, and they're very interested in whether those simulations are accurate and reflect reality well. This is going to be the first time we actually bump them up against hard data on what's going on in there. I'm almost certain, I'm very certain, they're going to learn something from that, and the simulations will get better. We're going to measure things at rates that have never been done before, and in places that have been hard to reach or even see because they go by too fast to be seen. So it's going to be fantastic.
You're talking about everybody working together, and that there is a way for, to be able to track things going around the heliosphere. What does that mean in practice? I mean, how are people actually collaborating? How can they work together?
Great question. Well, first thing is the data is public data. We don't keep the data for ourselves. We don't keep it just to the MMS team. As soon as the data gets to the ground, gets validated, make sure it's good data, it gets dispersed worldwide. It gets dispersed to our other heliophysics partners, and all of the other spacecraft that are working together. So as you said, you want to understand that system. As that solar storm comes towards you, you want to know about it. So the data from our other spacecraft are being fed to the MMS team. We coordinate. The MMS data coordinates a lot with one of our other spacecraft called Themis, another mission, which actually has 5 spacecraft, that will look at a global nature. So again, by having the data publicly available and sharing among all the other scientists that are operating our larger heliophysics system observatory, we can work together. And we actually do a lot of international partnerships, academic partnerships. It's scientists worldwide working together to solve these problems, where that's how we make our big advances.
Great, let's open it up to questions. Any questions from the audience here?
Given the dynamic nature of reconnection, how certain are we that we'll be able to observe one? How large is the observation area, and how long will we be observing?
We are very sure we will see. We are expecting about probably over the 2-year lifetime of a mission, about 100 events. We've had previous missions, one with our European partners called Cluster, for example, which looked at the larger scales. One of the things that you've heard is this, Glenn mentioned, was the electron scale versus the ion scale. The Cluster mission and also a little bit the Themis mission studied these larger scales. They never were not able to get down to what this black box. If you saw the science briefing yesterday, Dr. Birch showed you the diffusion, electron diffusion region, called this little small region. But so we know where these events occur from the larger scale observations. So we know that we have a very high likelihood over the 2-year lifetime to see a certain good number of events. We're expecting 100. How many we'll actually get, of course, we'll find out, but we're expecting many, enough to solve the problems that we need to have. The regions we are looking for, there's 2 main regions, one on the sun facing, we call it the day side of the sun. So as these events coming from the sun towards the Earth, they buffet the front of the magnetosphere, and we know that that's where magnetic reconnection occurs, and so we'll be flying through that. For the first part of the mission, we'll be flying through that region repeatedly. Then, as the solar storm or CME washes over the entire Earth, it actually buffets the magnetic field behind the Earth in what we call the magnetotail. And again, we know that that's another region from previous observations that magnetic reconnection occurs. That's actually a lot of times where the high energy particles that form aurora actually come from behind the Earth. They travel back down the magnetic field line. So again, we know they occur there. We've just never been able to sample them with the time resolution and spatial. That was the other part of your question, which you'll hear more about in some of the other speakers, is how fast we have to take it. We have instruments that are actually on this mission 100 times faster than we've ever had before. These are operating at 30 observations a second or so, because we are flying through these regions very, very fast. And we're actually going to be taking so much data that we're actually only going to be sending down about 2% of our data to the ground, because we're going to be taking a tremendous amount of data, and we have tools and people available to sift through the data to get the right data. So we store it on board, we get the right data, we send that down. So yes, the speed is, the temporal, how fast this occurs is very important to this mission.
Hi, I'm Michael.
Hi, Michael.
You've been describing incredible amounts of energy and a lot of the mysteries of what we know and don't know about what's happening in space. But what about all that energy and the implications on Earth? Are there connections that we know or don't know or studying between all this energy and the magnetic reconnection to things like volcanology, climatology, or meteorology, or other Earth sciences?
The most direct connections we have are what we call space weather. Space weather is actually the study of all of the things I've been mentioning. The starting from the sun, how they interact, these geomagnetic storms, the reconnection, all that energy released each sun, the flares, the CMEs, the storms, how they interact, these geomagnetic storms, the reconnection, all that energy released that you're talking about, we call that general topic, one of it is called space weather. And that has an effect on our technological society mainly. A solar flare, as happened yesterday, causes small radio blackouts, because the high energy particles came along and we had small, it wasn't tremendous. We all survived, so it's good. It's nothing dangerous. But we had small radio blackouts due to that. Larger storms and very large storms can affect GPS measurements. They can affect some of our communications. Airlines will occasionally divert their flight patterns away from the poles because, as you saw in that intro movie, where the aurora are, because that's where the magnetic field of the Earth comes down closer to the Earth, is near the poles. So that high energy particles coming down, they can interfere with communications, and so planes divert. And so that's another effect. Also on our power grid system, these, as you think of those on that image with the particles flowing along the magnetic field lines, just like the iron filings that Glenn was showing you there, but these are charged particles. What happens when charged particles move? It's called electricity. It's called a current. And when that current gets generated, that can affect currents on the ground, especially for long wires or long pipelines, which are made of metal and also carry current. And so you can have an effect on transformers, degradation of oil pipelines. And so we monitor this, and so that's kind of the effect that we have, these large energies have, I would say, is the largest effect.
We're going to have more questions as we go to the next ones. Thank you so much, Jeff. What we're going to do next is bring up our next two speakers. While we do that, I'm going to remind everybody we're going to get to our Ask NASA questions. We're getting some incredibly intense Ask NASA questions, so we're actually getting heliophysics people to make sure we can answer them as they go on. But I'm going to bring up our next two speakers right now. Come join me center stage, gentlemen. All right, so now we have Alex Young, who is a heliophysicist, and John Dorelli, who is a space scientist. Hello. Take it away, guys.
All right. So we're gonna get more into MMS now. We're gonna get into the nitty-gritty, and we couldn't be in a better position because we have one of MMS's scientists who's gonna give us all the dirt that we need to know about what's going on. So you go ahead. I was thinking maybe we would start with, what exactly is the magnetosphere, and how's reconnection related to that?
Sure. So as you've heard from Glenn, the universe is full of plasma, right? And the universe is also full of magnetic fields, and the plasma moves around and it carries the magnetic field around with it. And a great example of this is the sun. So the sun's outer atmosphere, the corona, is actually a 1,000,000-degree plasma, and because it's so hot, it actually expands out into interplanetary space at supersonic speeds, all the way out to Earth. So when it hits the Earth's magnetic field, you can think of Earth again, like Lynn was saying, is it's just this giant bar magnet that's rotating around space. So it has its own magnetic field, and the sun's plasma smacks into the Earth's magnetic field in the Earth's plasma, but they don't really want to mix. It's sort of like pressing two big balloons together. Something's going to give. And so what gives is that some fraction of that magnetic energy is converted very rapidly into plasma energy, and you get this enormous energy release and all the consequences, space weather consequences you heard Jeff talk about. So the reason this is great for MMS is because it provides us really an ideal laboratory for studying this process, because at the dayside boundary where the solar wind meets Earth's magnetic field, reconnection is happening there pretty much constantly. And we even have a pretty good idea from modeling where it happens. So we can actually tune the orbits, optimize the orbits, so that we maximize the probability that we're going to fly through this explosion, this magnetic explosion as it's happening. And so that's why MMS is really, a magnetosphere mission like MMS is really ideal for studying magnetic reconnection in the magnetosphere. And because this process occurs everywhere in the universe, we know that by understanding it in the magnetosphere, we're going to gain some insight into how it happens in other astrophysical contexts like solar flares and coronal mass ejections and gamma ray bursts and many other contexts in astrophysics. Yep.
So now let's zoom in on the spacecraft themselves. So you've got 4 of them, okay? And you're going to be looking at these 3-dimensional structures. But so why exactly do you need 4, and how are they going to be moving through the magnetosphere to give the kind of measurements that you need?
Sure, up to show a little bit about the orbit of MMS. And basically the reason that we need 4 spacecraft There you can see them there. They're flying in a tetrahedral formation. And as they go around the closest approach to Earth, it kind of gets stretched out. But the apogee of the orbit is cutting right across this magnetopause boundary. And as it reaches the apogee, it's in a sort of perfect tetrahedral formation. And the reason we like this is that, as Glenn was mentioning, the actual reconnection site is a very complicated multi-scale structure, and it's three-dimensional. And if we only had 3 spacecraft, well, then we have a triangle, and that's basically giving you a plane. You might be able to project things into that plane and get some information, but you're losing a lot of information. So to get that third dimension, we need to have at least 4 spacecraft. So that's why we have the tetrahedral formation.
So what's in terms of the instrumentation, okay, that you're going to need to make the measurements? What is special about the instrumentation on MMS? What's unique in relation to previous missions?
Yeah, so that's actually one of the most exciting things about MMS is that, as we heard, this is really a small region that we're trying to cover. The electron scale region can be as small as 1 kilometer, which, on Earth seems like not a small distance, but on the scale of the magnetosphere, it's microscopic. So it's really hard to catch this. And to make matters worse, the magnetopause boundary is moving back and forth. It could be moving back and forth at about 100 kilometers per second. So that's very fast. So we need, as the magnetopause moves across this tetrahedron, we have to be taking really sort of like high-speed photographs of this explosion as it's happening. So we've had to make our particle instruments, the instruments that are actually collecting the particles that are being accelerated by this process, about 100 times faster than they have been on previous missions. So on previous missions, we, even cluster that had 4 spacecraft, we have to wait for the spacecraft to spin around in order to get a complete picture of the sky, and that takes about 3 or 4 seconds. Well, we don't want to wait that long, because by the time the spacecraft spins around, you've just lost the event, right? You're going to get a very blurred picture of what's going on. So instead what we do is we have a bunch of these spectrometers arranged all around the spacecraft, and they're all looking simultaneously at different locations in the sky, and they're making very rapid measurements of the particles. So we can get like a 30 millisecond snapshot instead of a 3-second snapshot. And so that's going to allow us to actually see, kind of like high-speed photography, this explosion as it's happening. Hopefully we're going to catch it within this tetrahedron.
Well, I know you're probably most familiar with the FPI instrument, okay, because that's something that's coming out of Goddard. So can you tell me a little bit more about it specifically, and tell me how many of these did you actually have to make?
A lot, actually. And so I was not personally, so my expertise is actually in computer modeling and simulation, and I'm not the guy that's in the lab actually building the instruments. And so there was a large team of scientists and engineers actually building these things. And it was an incredible challenge, because usually you build maybe 1 or 2 or 3 of these things. And we had to have 4 spacecraft, and each of them had to have 4 spectrometers around the spacecraft for electrons, another 4 for ions, right? So we've got 32 spectrometers that we have to build. And then not only that, but calibrating one of these things once the data starts coming in to make sure that you're actually getting the right answer, it's very challenging even with 1 of these. So now imagine you've got 32 of these and you're trying to intercalibrate them all. So it's an incredible challenge, and it's going to be extremely exciting once we start getting data down. We're going to see really new stuff.
So one more thing, one of the things I'm really curious about, for you, what is the most exciting? If you can actually narrow it down to one or a few things, what's the most exciting thing about this? What really jazzes you up about this mission and gets you excited about it?
Well, like I said, I mean, my training is as a theoretical physicist, and I kind of grew up as a scientist studying reconnection. And back when I was a graduate student, there was a lot of controversy about what was going on, and people had all kinds of theories about what's going on. And it's sort of matured now, almost, gosh, it's already been 15 years. 15 years later, to the point where we have some pretty good ideas, and we think we understand what's going on. And now we finally have this mission that's going to test some of these ideas that I kind of grew up around, and I find that extremely exciting. The other thing is, being a theorist, We don't really get the opportunity to have a front row seat to the full life cycle of a mission like this and see the hardware being built and get to talk to the engineers. And that's been really an exciting thing for me, because I think I can get, I have a different perspective on it now. I can see both the abstract theoretical side of it, but also the practical engineering side as well. So yeah, that's the most exciting thing for me.
Cool. Well, one of the things we talked a little bit about this earlier, because you do work in computer simulations. So I was thinking, maybe why don't you mention a little bit about how is this related to? You've actually worked with looking at magnetospheres of other planets. So how is that related to MMS?
Oh yeah, good question. So Earth is not the only planet with a magnetic field. We've got Mercury that has a magnetic field, and another interesting magnetosphere in the solar system that you might not have heard about is the Jovian moon Ganymede. Jupiter's third moon. It's actually the only moon in the solar system that has a magnetosphere, and it's the smallest magnetosphere. And these are the only ones that we can actually fit onto high-performance computers that actually have some of the physics in it that MMS is going to measure. We can't yet do a full-scale Earth-size magnetosphere. So we've been able to learn some new things about the global consequences of some of the MMS physics that we're going to be measuring. And we're going to be able to test some of these simulations with MMS.
We're going to keep you both up here and answer a few Ask NASA questions. We've got one of them over there. Go ahead.
Indeed. So first question comes from Twitter user Joey, who asks, where will the reconnection events be happening in relation to the formation flying MMS spacecraft?
I'll take that one. So like I said, on the day side, where the solar wind is running into Earth's magnetic field, it's pretty much happening continuously. And we have a pretty good idea of how to predict where it's happening based on the orientation of the solar wind's magnetic field relative to Earth's magnetic field. We have some good ideas about where we expect to see reconnection happening. So that's where we think we're going to get our earliest sort of low-hanging fruit in our first good science. By the time you get out into the tail of the magnetosphere, it's a little more complicated, because what happens is you get reconnection on the day side, and some magnetic energy gets transported to the tail. It's sort of like a wake region, you can think of it. The magnetosphere is sort of bullet-shaped, and the field lines drape around. But then you get another buildup of magnetic energy in the magnetotail. And it's a lot more difficult to predict when and where reconnection is going to happen there. That's going to be a more challenging part of the mission. And so what we're doing is, because MMS is collecting data so rapidly, we don't actually have enough telemetry bandwidth to bring it all down continuously. So what we have to do is we have to try to be clever about it. We have to do some onboard statistical analysis to try to figure out what is the data that we want to grab. And for the day side, like I said, we have some good ideas about how to interpret that statistical analysis to tell us when we need to bring the data down. But we're going to have to do a little bit of work. We're sort of flying by the seat of our pants a little bit on the tail, because we don't exactly know where and when the reconnection is going to happen. We have to be a little more clever about it there.
And we have another Ask NASA question.
This one comes from Twitter user John, who asks, are the probes in any danger when a magnetic force line reconnects?
No. No, there's no danger of as has been mentioned before, we quote these huge energy releases, but really what we're looking at is a very microscopic region. And so most of the large energy releases happening in a more global region, the magnetosphere. It's when you integrate over the magnetosphere that you get these large energies. But the particles that we're actually collecting from the reconnection process are well within the safety parameters of the instruments, right? I mean, the instruments were designed to collect particles of those energies. And they go up from about 10 electron volts to about 30 kilo electron volts. So it's pretty low energies.
Okay, we have a question from someone here in the room. Here, yeah, hold on one second. And stand up if you don't mind.
Right. The launch opportunity assessment report mentioned conflicts between the science goals and the engineering goals of building the spacecraft. I was wondering maybe what some of the science goals had to be compromised in order to build the actual spacecraft.
Oh, so I don't know the specifics of what you're talking about, but that's sort of what I've learned.
That's a fact of life for all missions. I mean, scientists have these great dreams of what they want to do, and then reality sinks in, and they have to do what is physically possible and what they can afford.
And I think we have a reality check. How are you guys doing? Is everybody good? Everybody's so silent at a NASA social because everybody's focused completely looking down, going over and going through their phones and looking at everything and retweeting everything. For hashtag NASA,
I just wanted to say first that Paul Kastick is my former student. And I'm very proud of him. Yeah. So I'm gonna stand up here. I like standing better. I'm gonna take you out beyond the sun. So we're going from the sun. We're going out past Earth. We're going out past all of the planets, and we're heading out. And finally, we come to the interstellar medium. Now, do you know what the boundary is called between the plasma and magnetic field from the sun and the interstellar medium? Does anybody remember what that's called? Yes, that's the heliopause. So there's a heliopause out there, which is the boundary between the solar system and the interstellar medium. Now, from a lot of measurements and things, we had a pretty good idea about the direction of the magnetic field in the interstellar medium. And that's going like this, say. And then here's the solar magnetic field from the sun, spitting out from the sun and the solar wind. That is going this way. So here's this interstellar field, here's the solar field, and there they are. And what's going to happen? What's going to happen when here's the interstellar field and here's the solar field coming together? Sorry. What's going to happen out there? Magnetic reconnection. Okay, so some of you may remember that in the summer of 2012, the Voyager 1 spacecraft crossed the heliopause. And there was a lot of fishy stuff that happened at that time. A lot of stuff was bouncing up and down, and the present interpretation of what was going on was that there was a magnetic reconnection going on at the heliopause, and Voyager passed through those regions. Okay, so, well, what does that mean? Well, it means that nice, perfect interface that we thought we knew about, the heliopause, was not quite so perfect because it was all broken up because there was magnetic reconnection going on. And what's interesting about that is galactic cosmic rays. Now, in some sense, the heliopause acts like a bit of a shield for some of those cosmic rays, and they get diverted around. But the magnetic field, if it reconnects, breaks things up, and that allows stuff to leak through. So we're still trying to understand how do galactic cosmic rays actually get through the heliopause. So we really want to know what that heliopause is. And so that's one interesting aspect of reconnection, which is now in the outer heliosphere. Okay, so now I want to take you beyond that into the universe as a whole. There are lots of explosions in the universe. They're not all produced by magnetic reconnection. Clearly, gravity plays a major role. When stars burn out, they collapse. You have supernova explosions. A lot of explosions like that. But there are regions with extremely intense magnetic fields throughout the universe. An example is when you have a star collapsing, it can go down and form a neutron star, and there's certain neutron stars called magnetars, which have magnetic fields which are like 10 to the 15 power Gauss. Now remember that the Earth's magnetic field is about a half a Gauss on the surface. These magnetars have fields of 10 to the 15 Gauss. That's a pretty intense field. And these things have flares, just like on the sun. And sometimes we see them. And there was a flare a few years back from a magnetar which produced an energy, I think it was like 1/5 of a second long, and it produced the output of energy equivalent to the sun emitting its power for, I think it was like 200 million years of that order. That is a lot of energy coming out, and it's from these intense magnetic fields. There are lots of other regions too where we have intense fields. Another example is around black holes. You heard that mentioned earlier. And the way this happens, you've got a black hole which could be extremely large, 1 million times the mass of the sun. And those black holes accrete matter. And that means that matter falls into these black holes. And what happens is it starts falling in and it starts spinning around the black hole. So this black hole has got this accretion, what's called an accretion disk, spinning around. That accretion disk is very turbulent, and it produces magnetic field. And so as it falls in towards the black hole, it spins that magnetic field up. And you can imagine wrapping and wrapping that field over and over again until that field becomes very powerful. And then it shoots out like a spring being released. And it forms these jets. And these jets can go huge distances, 100 light years. That's a huge distance going north, south from these accreting black holes. Now, in astrophysics, the astrophysicists never really were that enthusiastic about magnetic reconnection, believe it or not, because they were convinced that shock waves were producing most of the energetic particles. Okay, so what I want to do is show you what really changed their minds about all this. And I think there's been a big transformation in the thought of astrophysicists about the role of reconnection. And so what I want to show you is the Crab Nebula, if we can have that video up on the screen. Now, so there's a picture of the Crab Nebula. This comes from a collapsed star, and it was seen by astronomers on Earth way back in 1024 or something like that. So here you're seeing the magnetic field wrapped around that Crab Nebula. It's now a pulsar, which means it pulses out. And you can see the jets forming north and south, just like I was describing from the black hole. This is not a black hole. And so it's coming back now to the real picture with real data of the crab. Okay, so now what happened in this case was the Fermi Gamma Ray Telescope. And what they saw from the crab was this very powerful flare from the crab. And this happened like in one day. And it was very energetic gamma rays. And there was just no way in the world that a shock could do that. And so the astrophysicists were surprised, and now everybody is working like mad on magnetic reconnection to try to figure out how this crab flare happened and how to explain those very energetic particles. Okay, so now we're faced with a conundrum, and that is you're looking at a crab flare. It's a long way away, and in fact for the crab flare, they don't even know where on that nebula that flare took place. And so if we want to understand the details of reconnection, how you produce energetic particles, it's not so easy to do with the crab flare. And that's where MMS comes in, because in the magnetosphere is right now, at least for now, the only place in the universe where we can actually go in and measure what we have to measure to figure all this out. And so we're going to try to do that with MMS, and that's going to have implications for from the broader context of astrophysics.
All right, fantastic. So let's take some questions. Do we have any questions from people here in the room? All right, right here. If you don't mind standing up.
Is there any science on this mission that can be used? Is there any science on this mission that can be used to further our manned space program?
Do you know what he meant?
It's the dreaded
Let us
electronics
think.
question, right?
Oh, yeah. Do you want to try it, or I can do it? Go ahead. Go ahead. No, go ahead.
I don't think so.
Oh, okay. So, yeah, no, I want to say something. So I do want to say something. You know, astronauts out in space are in a risky environment. It's risky because of energetic particles. And so one of the things we need to monitor is what's going on at the sun. If there's a big flare, it's very dangerous because of the high energy particles. And so we're trying to understand how those energetic particles get produced on the sun. That has implications for being able to predict when will you get an X-class flare, which could put our people in space at risk. So it's got enormous implications from that point of view.
All right, hold on. We have Alex Young with not a rebuttal, but
No, that was great. I was just going to add one thing that's important about this is that when we study things like CMEs, we have some warning. So these energetic particle events, just like the flare, when you see the flare is here. Those particles are traveling near the speed of light, so you don't have a lot of warning time. So it's critical to have this forecasting ability for these particles, and that's a really, really, really hard problem. So just following up with what you said.
Great. I'm ready to answer a bunch of Ask NASA questions here as well, because I know it seems like for every question we get really like 3 excellent answers about it, but we've been getting a slew that have been